All right, here's 4-3. We're just going to spend a day on it. Typically stuff that we're pretty solid with and know fairly well. Usually the term I find that most of you apply to this section of what we would call right triangle trigonometry problems, which are ones that are actually taking place within a right triangle that could be constructed like a diagram. I find most just call it SOHCAHTOA, okay? A little acronym here, because we kind of, the ratios are all the same, but we just kind of use different terminology. Instead of X and Y and R, which we'll actually get back to in section 4, we start to use these terms like opposite over hypotenuse. Okay, and in a minute, I'm going to use this example, this triangle right over here. I'm going to say that angle is 45 degrees. And then for cosine, the AH is from adjacent over hypotenuse. And then good old tangent is opposite over adjacent. And of course we have our others, cosecant, but keep in mind these are all reciprocal ratios. Whoops. Shouldn't be over adjacent. It should be hypotenuse over opposite. And here's secant. Which would be hypotenuse over adjacent. And of course cotangent. Adjacent over opposite. All right, now I want to show you one thing here. All I want to do is just quickly look at the cosine value of 45 degrees. Because we did this before, but I used 1 as the hypotenuse, and now I'm going to say the legs are 1. And with the Pythagorean theorem that you would get that it's the square root of 2. Okay? What I want to show you here, because if I use adjacent, which is right here, over hypotenuse, which is there, I get 1 over square root 2, or square root of 2 over 2 when I rationalize it. Okay, I know we know that that's the cosine value of 45 degrees, but the point that I'm trying to make is the side lengths don't matter. All right, I mean they do, but the trig functions are all about ratios. How did the length of this side compare to this side? Okay. If it's a 45-degree angle, that ratio is going to be exactly the same. All right, which is why I wanted to show you with a 45-degree, even though the side lengths are different, we get the same cosine value because we have the same ratios. Okay, let me show you one more. This is how we constructed a 30, 60, 90 triangle. But now let's say, before we said the side lengths were 1, let's say, right, that's going to be 60, that's going to be 30. Okay, let's say they're 8. That would be 8, and then this part right here would just be 4. Okay? Let's look at the sine of 30 degrees, which again from our study of the unit circle, we know it's a half. Okay? But here I made the side lengths of this equilateral triangle 8 times as long. But notice what happens is my opposite side has a length of 4. The hypotenuse has a length of 8. The ratio stays at a half. That's a really good one to look at because it's one of the easier ones to describe what's going on with the sine value. if you're in a right triangle and you are looking at it from the 30-degree angle, the length of your opposite side will always be half as long as the hypotenuse. Okay? Doesn't matter exactly what the numbers are. Okay, as far as how long those side lengths are, that's going to be the ratio. All right, so here is theta. Okay, I'm going to give us some nice easy numbers to start with and say that the two legs are 3 and 4. And if you apply the Pythagorean theorem, you'll see the numbers come out beautifully and that the hypotenuse is 5. All right, so if we can get a diagram set up like this, okay, and the numbers may not be as nice. You might have a square root that you have to rationalize. But I would expect if you can get that diagram set up, that you could look at it and see from theta that the sine value is 4/5. Cosine is 3/5. And then tangent is 4/3. And of course, don't forget about our reciprocal. That means cosecant is going to be 5/4. The secant value of that angle is going to be 5/3. And our cotangent value is going to be 3/4. Okay? So that's one approach to take to getting the values of all 6 trig functions, is to set up a diagram and to do it that way. Another approach to take is to use what are called identities. And now we're really going to get pretty serious with identities in Chapter 5, but I want you to see them. I don't know if I can fit them all on the screen. I think there I've got it. Reciprocal ones, you use those all the time. That's just saying that if you flip the value of the fraction that you get the reciprocal trig function, like sine and cosecant. The quotient ones we'll use all the time. I'm going to do an example in a minute with one of those. And then the Pythagorean identities as well. Okay, but I want you to see them now and to show you what you can use them for. Okay, so notice the same kind of problem. I'm going to do 2 of them here that involve trig identities, but my goal is going to be the same, okay? Because I really want to illustrate here what trig identities do. Is it's basically like the problem with the diagram where you want to find trig functions, but you do it without one. No diagram needed, right? So let's the sine value of this angle, I should have a theta in there. It's 0.6. What's its cosine value? Okay. Now you could certainly draw a diagram if you wanted, right? But the identities represents really a more of kind of an algebra approach to take. If you wanted to do it that way, as I could say with my identities, that the cosine value that I'm looking for plus the sine value, well, the cosine value squared plus the sine value squared has to equal 1. Well, just doing a little bit of solving, I would get, that this has to be 1 minus 0.36, because that's 0.6 squared. Cosine squared is 0.64. And then my missing cosine value is 0.8. Okay, notice no diagram. I just had a formula, plugged in some values that I knew, and I went ahead and solved. That's kind of the approach that you take with the identities. Let's say now, after all that, we're still talking about the same angle. What's its tangent value? Well, here it's probably easier to just say, instead of drawing a diagram, that tangent is sine over cosine. Well, I know the sine value of this angle. I know the cosine value. That's 0.75, and there's your tangent value. Okay? Now to kind of bring this full circle back to the whole diagram thing, let's say this is our triangle. Let's say there's theta. Okay? It started by giving me a sine value, which means the opposite side over the hypotenuse is 0.6, so I could say 0.6 over 1, and then I could have used the Pythagorean theorem to get that this side is 0.8, and then we could have gotten all of them like we did in the problem with the 3, 4, 5 triangle. Okay? It's kind of a non-diagram approach. Let's try one more, because I want to use a couple of the different identities. Now we are assuming, one thing that's worth noting is the angle that I have to begin with, I'm assuming it's less than 90 degrees, right? Because I'm saying this belongs in a problem that could be set up as a right triangle, which means theta has to be less than 90, okay? So let's say that tangent is 3. Here's one where, because I typically say, do you want to take the diagram approach or the identity approach? That's really up to you as to how you like to solve these problems. This is one you'd probably, if I wanted to get the cotangent value, I would just go do a third, 3 over 1 and flip it to get a third. I don't think you'd want to draw a diagram in that case. Now let's say from all this we want to get theta's secant value. Well, one of the identities states that 1 plus an angle's tangent value squared equals its secant value squared. So the secant value squared would be 10, and then secant of theta would be the square root of 10. Okay? Once again, to relate it back to our diagram, let's say theta was right there. Okay? It told us that tangent was 3 over 1. That means this opposite side would be 3. The adjacent side would be 1. With the Pythagorean theorem, we'd get that the hypotenuse is the square root of 10. And now you can kind of visualize your opposite adjacent sides and your hypotenuse. Okay? Again, the big idea here, a diagram approach or more of an algebra approach. That's really the difference between the diagram and the identities. A quick word on your calculator with trig functions. It's pretty straightforward. I don't have a calculator screencast to show you right now, but just a couple of important notes. Under the mode button, be really good about checking to see, are you in radians or degrees? Okay, if the calculator is going to not, work out well, that's probably what's happening. Okay, so be sure you're really clear as to which you're supposed to be in. Right now, once you have that, it's pretty straightforward. Right? If you wanted to get the cosine of 28 degrees, okay, you would literally just type in cosine of 28, making sure you're in degree mode. Okay, switch over to radians if that's what you're supposed to be in. Okay, and this would come up, by the way, if we're dealing with an angle that's not on the unit circle, nor can we relate it back to an angle that's on the unit circle. We're going to get a decimal approximation if we do it this way, which is, if we're doing it, it's an angle that we don't have any other options. That's just where we have to go, like 28 degrees. There's no way we can get that back to the unit circle. Now, you might notice there's no secant button. It's because we don't need one. If you use a reciprocal identity, that would be 1 over the cosine of 28 degrees. You could apply the same thing for cosecant and cotangent. Okay, that's the approach that I would take if you're going to evaluate one of those. All right, we've got 3 little word problems left here. All just involve kind of various levels of right triangle trig. Here's the Washington Monument. We're going to get an estimate for its height. We're going to assume it's a right angle with the ground. This corner of the triangle is where we are. Our angle to the top is 78.3 degrees, and we're 115 feet away from the base. And we are after h. Okay? Now, on one of these problems, they don't really vary in terms of how they're solved a whole lot, but the trickiest part can be, how do you make sure you're picking the right trig function? Well, I'd look at this and say, I got to find the height, so I need that side. It's opposite. I'm 115 feet away. I know that side, so I'm probably going to use that too. If I look back at my list of my trig ratios, I see that tangent is going to be my winner. That's opposite over adjacent, so I'd say that the tangent of 78.3 degrees equals the height of the Washington Monument divided by 115. And once you have that, they're not bad at all to solve. Now, here we come to kind of our first case where we've had to make the decision of, tangent of 78.3, is that an angle we're going to get an exact trig value for? Or do we have to go to the calculator to get a decimal approximation? This one's kind of, if you're dealing with an angle that's like a decimal, like 78.3, calculator's a pretty safe bet. Comes out to be 555, and problem solved. I said these problems can't vary a whole lot. Here's one where they will a little bit, because there's something about this one that's just kind of fundamentally different from the first that we just did. And it's what you're trying to find. It's not a side length. It's an angle. You want to know what angle that is right there. Now here's what I know about my angle. I know that the opposite side is 200 yards and the hypotenuse is 400. And if you were to look back at your list, you would see that that is the sine ratio. So I don't know what this angle is, but I know its sine value is 200 divided by 400, which I am going to go ahead and simplify to a half. Okay. Now, theoretically, you can get this off the unit circle, and you probably should. Okay, that may not be the most common way that we get this, because what we're the part of trigonometry that we're getting to right now is the need for an inverse trig function. Okay, as always, whenever we talk inverse, you should think backwards. Okay, trig functions go from angle to trig value. Inverses go from trig value to angle. Okay. Now I'm guessing you could take this and be like, all right, I'm looking for an angle, right? You know, if you're going into to the unit circle, you're going to be in quadrant number 1. That's where all of these problems have been. You know, where in quadrant 1 do I find an angle that has a sine value of a half? And you will see at 30 degrees, you'll find it. Okay, you'll find it and you'll be good to go. Okay, we'll talk about this much more as the chapter progresses. But if you hit second sine, you'll get something like that on your calculator. Because again, the calculator isn't going to work for every inverse. That would do it on the calculator. Okay, if you hit second sine, now your calculator is switching it, and it's expecting you to give it a sine value. And then after you do that, it will give you an angle. the angle that you're looking for that has the sine value that you typed in. In this case, it would be 1/2. All right, last problem of the lesson here. We've got this skateboard ramp. And we are after the length of this side. We're looking at it from that angle. Here's the opposite side. There's the hypotenuse, right? And now I want to talk about a couple different ways that you could do this, right? Because I know with opposite and hypotenuse, most of you would set it up like this and say sine of 18.4 degrees equals 4 over c. And that is a perfectly acceptable way to do it, but now I'm kind of being picky here. And the one thing I don't like about this is the variable is on the bottom. So then to get c by itself, it takes 2 steps of solving. Instead of 1. Okay, which that's not a big deal, right? 2 steps, that's really not that bad. However, it wouldn't be my first choice if I can find a different mathematical method where I could, find it more efficiently. All right? And I want to bring this one up because if I don't, these never get used. Okay? Is there a way that I could set it up so that the variable would stay on the top and then 4 would be on the bottom? Kind of like the Washington Monument problem, which would just involve multiplying both sides by 4, and there is. This is where a reciprocal trig function can be kind of nice. If I had used cosecant instead of sine, then the variable for c, or the unknown for c, I should say, would stay on the top, and I can just do 4 times cosecant of 18.4 degrees, and that is the length of your skateboard ramp, which would be about 12.7 feet. Okay? One final word with this problem, like right here, you would have to go to the calculator. Don't forget, if you want to do cosecant of 18.4 degrees, you would need to type that in as 1 divided by sine of 18.4 degrees. But either method here is going to get you the same answer of about 12.7 feet.